Okay, welcome everybody. Today is going to be the last lecture of our algorithmic meta theorem lecture. So I guess we're going to start with a few announcements. So yeah, today's the last lecture. On Friday was the last exercise session. So we're nearing the end of this course. That's why we're also going to take a little bit of extra time today. So in order to wrap up everything in this year, I may need 30 minutes extra today. If you have some stuff afterwards, of course, everything will be recorded and uploaded so you can watch it afterwards. So yeah, then this is the last lecture. So I would also write some feedback. That would be very helpful for me if you could fill in the short anonymous survey that I provided on Google and tell me what you liked, what you disliked, in particular, where you see something that can be improved. That would be very nice to hear. Okay, besides that, in January or February, there will be the oral exam. So if you want to register for the oral exam, please write me an email. So if you participated in all the exercises, you will get mark 3, befriedigend, and then if you want to take the oral exam, this grade can change. It can change for the better and for the worse, but hopefully for you guys all for the better. And just maybe as a quick guideline, what to expect in the oral exam. So I will ask you some questions about what happened in the lecture. And if you're trying to go for a grade good, a grade 2, then I guess you should be able to understand and recall all the definitions that we encountered during the lecture so far. So in particular, something like the exercise, like the first exercise of the last sheet, where you should determine which graph classes were closed under adding apex vertices. This is something that you expect to solve, because there you have to recall all the definitions of the various graph classes and their properties. And yeah, you should have at least such a high level understanding of what is going on. And then if you're aiming for sehr gut, a grade 1, you should also be able to understand at least what happened in all those proofs that we discussed so far. Of course, you don't need to understand every single last detail, but at least the high level structure, you should be able to retell it and argue why we did what in the proofs. And so yeah, if there's any questions about what will happen in the oral exam, you can also always drop me an email, and we will have like a quick question session sometime before the oral exam, probably in January maybe. We'll have this question session where you can come and just ask anything that's on your mind. Okay, are there any questions about the organizational matters so far? Okay. Great. Then let's maybe move on. So in the last lecture, we started proving that you can do first-order model checking on graph classes with bounded expansion. In particular, we're showing that if you have a graph from a bounded expansion class in the formula phi, then you can evaluate it in a linear FPT running time. That is some function of the length of the formula multiplied with the size of the graph. And yeah, this proof was not quite complete. We dealt with quantifier elimination on trees, and today we're gonna wrap it all up and also do quantifier elimination first on bounded tree depth and then also on bounded expansion. And after we've done this, we will wrap up this whole theme of sparsity. We will quickly talk about nowhere dense graphs as well, and then we're gonna talk about dense graphs. So all these graphs that contain large cliques, for example. And there this theory is way less developed. That's why I still want to give you like a brief overview of what's currently the active area of research when it comes to dense graphs. Okay, but first let's talk about bounded expansion model checking. And in the proof that we started last week, we were working with functional graphs. So instead of having an edge relation, we now had functions that map one vertex to another vertex. And we used these functions to represent edges. For example, if we want to represent an edge from a vertex D to a vertex B, we can draw a function like this that goes from D to B. And so yeah, functions map vertices to vertices. And we showed that these functional graphs, that they can model bounded expansion classes. And of course, we also allowed colors on these graphs, so you can have these unary functions. And as a technical tool, we also allowed nullary relations. And so yeah, if you have these functional graphs, you can easily translate them again into normal graphs. So the Geifmann graph of a functional graph is simply the graph that you obtain from this picture on the left by directing or forgetting the function symbol and the direction of the edges. So you add an edge between u and v if and only if there's some function that maps u to v or v to u. That's what we call the Geifmann graph of a functional graph. And then we can say that the class of functional graphs has bounded expansion if and only if the class of the Geifmann graphs has bounded expansion. In last lecture, we convinced ourselves that it is sufficient to do model checking on bounded expansion functional graph classes. And how did we proceed in our model checking algorithm? We did something called quantifier elimination. And quantifier elimination takes a formula with one quantifier and maps it to a formula with 0 quantifiers. And in the process, it changes the graph a little bit by adding colors. So we start with what we have here on the left. We have some functional graph G, and we have a formula phi that depends on y and x bar, and the variable y is quantified. So the free variables are x bar in this formula. And the quantifier elimination procedure, it creates a new tuple. It consists of a graph G prime and a formula phi prime. And the very important thing is now that the formula phi prime, it should be quantifier free. So we have effectively eliminated this existential quantifier over y. And what remains is only the free variables x. And we want these two formulas to be equivalent in the sense that no matter what you plug in for x, so if you take some tuple v bar and plug it in for x bar here, or plug it in for x bar here, and then you evaluate the left formula on the left graph and the right formula on the right graph, you get exactly the same answer. So we consider these formulas to be equivalent if they're equivalent no matter what you plug in for the free variable. And we had some further technical details that are quite important. And this is that the length of the formula phi bar, it needs to be bounded by the length of the original formula. So the formula, of course, cannot explode in size. That would be very bad. The size needs to be bounded as a function of phi. And additionally, we want the graph G prime to be also sparse if G is sparse. So we enforce this by requiring that G prime and G have the same Geifmann graph, and G prime may additionally add some colors to the graph, but it cannot add any extra edges that were not there already. If you want to make this a little bit more formal, then we say that a graph class C has a quantifier elimination procedure if we can do the following. So you get as input the formula exists Y such that phi holds, where phi is quantifier free. And you say if you get such a formula as input, then there also always exists a formula phi prime with the following properties. Additionally, you want that for every input graph G, you can compute in linear time another functional graph G prime with the same Geifmann graph as G. And you want the input graph and input formula to be equivalent to the output graph and the output formula, which means no matter what tuple v bar we take, if we evaluate phi with v bar on G, this is equivalent to evaluating phi prime with v bar on G prime. This is what we call a quantifier elimination procedure. And if we have such a thing, then this automatically gives us a model checking algorithm. So let's say we want to do model checking for such a formula, we bring it into pre-next normal form, and then we look at the innermost quantifier-free formula. So here now, this is a formula on the variables x1, 2, 3, and we have the innermost existential quantifier quantifies over x3. This x3, this will be our y, and then we have this formula that depends on y, and the x1, x2, this will be our x bar, so we can write it as phi of x bar y. This is how we match the variables in this setting, and the quantifier elimination procedure then effectively eliminates the y or the x3, and we get a new formula that depends only on x bar, in our case x1 and x2. And we repeat it using De Morgan. This also works for universal quantifiers. Repeat it until we're left with the quantifier-free formula, and this is something that we can evaluate easily. So it's a sentence that is quantifier-free, so it can only contain these nullary function predicates. And so last lecture, we did such a quantifier elimination for forests of bounded depth. This was a bit of an involved proof that we showed there so far. We were considering these ancestor trees and using colors to encode whether certain children are present in the ancestor trees or not, and counting them. But yeah, this is something we completed, and I don't want to go into too much detail of this, but I want to use this now as a black box to also tick off the next two things. So we're going to use this to show quantifier elimination for graph classes with bounded tree depth. And then we're going to use low tree depth colorings to also lift this result up to bounded expansion. So let's start with the case of bounded tree depth first. And again, if there's any questions in between, feel free to interrupt. Okay, so the precise statement that we want to show is the following. We have a class C, functional class, whose Geifmann graph whose class of Geifmann graphs has bounded tree depth. And then I want to show that there is a quantifier elimination for this functional graph class C. And just a quick reminder, what was tree depth again? The tree depth of a graph is the minimal height of the graph, of an embedding of a graph into a tree, such that edges go only between ancestors and descendants. So here, this graph has been embedded into a tree. The tree looks kind of like this. You have this edge. That's a tree that it has been embedded into. And we see that these functional edges, they only go between ancestors and descendants. And such edges between siblings, they are not allowed. And they're indeed also not present in this embedding. So this would be a valid embedding that would show that this graph has tree depth equals 3, because there's 3 layers in this tree. And now we want to do quantifier elimination for these kind of graphs. And we're going to do this by reducing it to the case where we only had trees of bounded depth. So we're going to take a graph with bounded tree depth and map it to a tree of bounded depth. And the tree will again be a functional graph. So the quantifier elimination procedure again, we have a formula phi and the graph D, and we're going to map this to another formula and graph phi prime and G prime. And G prime will be a forest of bounded depth. Where G had bounded tree depth, G prime is now a forest of bounded depth. So G prime will be even simpler than G, but we will not, in this very first step, we're not doing any quantifier elimination. We just replaced phi with phi prime, but there still is this existentially quantified variable y. So we're not done yet. So far, we only made the graph a little bit simpler. So we map from this graph here at the bottom with bounded tree depth to another graph that is now a functional forest, it's drawn here in orange. And we still have the quantifier, but G prime now is a forest of bounded depth. And here we're going to use the result from the previous lecture about quantifier elimination on forests of bounded depth. So this is now fine. On this forest, we can do quantifier elimination, and this gives us a new forest, G prime prime, and a quantifier-free formula phi prime prime that holds if and only if the original graph with bounded tree depth and the original formula holds. There's one issue here. We require that these two graphs have the same Geifmann graph. They should have the same Geifmann graph. So the quantifier elimination for trees, that one preserves the Geifmann graph. But the important step is if we go from the graph with bounded tree depth to the forest of bounded depth, we need to make sure that the Geifmann graph of G prime should be a subgraph of the Geifmann graph of G. If this is fine, then we can, then also the graph G prime prime will be a subgraph of the Geifmann graph of G. And this is something even better. If G prime prime is a subgraph of the Geifmann graph of G prime prime is a subgraph, then we could just add some meaningless edges, and then they also have the same Geifmann graph if we want that. So the key step is now mapping this graph with bounded tree depth to the forest of bounded depth. And this is what I want to describe next. So we start with the Geifmann graph of G. So we're going to forget the orientation and the labeling of the edges, and we just have this Geifmann graph here at the bottom. This is a normal graph, and we can do normal graph operations on it. For example, we can build a depth first search tree on this graph. So we're going to start here at an arbitrary vertex and going to do a depth first search. And this gives us a tree. And we can turn this tree into a functional representation. So we're going to pick the root of the depth first search tree as the root of our functional graph. It's here. And then we're going to add the parent relation in a way that it always points to the predecessor. And if we have a root which doesn't have a predecessor, then it points to itself. So now this is our forest. We notice that every edge that is in the forest is also contained in our input graph G. So the forest is a subgraph of the graph G that we're trying to simulate, or whose information we want to encode. But so far, we don't know anything about the depth of this forest or this tree. So we require that this orange graph should have bounded depth, because otherwise we can't do quantifier elimination. And now a very nice statement becomes useful that we showed in the last exercise and talked about last lecture. We showed that a path of length n has tree depth log n. And if you reverse the numbers, you notice this implies that if you have a graph with tree depth at most d, then it cannot contain paths that are longer than 2 to the d. So in particular, any path in the depth first search tree that we just built has length at most 2 to the d. So also all the paths from the root to the leaf, they also have length at most 2 to the d. So the functional forest that we've built has depth at most 2 to the d. So if d is the constant, then also 2 to the d is the constant. And indeed, the forest that we've built comes from a graph class of functional forests of bounded depth. So that is very nice. But there's still all these other edges in the graph that we haven't encoded yet into our forest. And this is what we have to do next. And in order to do that, we notice some nice properties of these edges that we want to encode into the forest. So all the edges that are not in the functional forest, they go between ancestors and descendants. So this edge here goes from the vertex at the bottom to the vertex at the top, and the vertex of the bottom is a descendant of this vertex at the top. So I want to convince you that there cannot be any parallel edges between vertices that do not stand in an ancestor-descendant relationship in this functional tree. And in order to convince you of that, let's assume for contradiction that there is this edge between two vertices, maybe U and V, that do not stand in ancestor-descendant relationship. And let's see what the depth-first search tree would do. The depth-first search, it would start here at the root, and then it would go down the tree, and it would go down, and at some point we reach a vertex where we cannot go further anymore in a depth-first search tree. So we backtrack, and we go up again, and then we go down again. Maybe we go further down, and again we backtrack, and then we go up again, and maybe we go down again, and we go up again. And now we're at U, and we notice that the depth-first search tree, in this case, backtracked to the vertex W. But because there's this edge here, this horizontal edge between U and V, the depth-first search tree will not backtrack. It will put the edge UV also in our depth-first search tree. So any edge that occurs will be taken greedily by the depth-first search algorithm. And this shows that such an edge UV between vertices that do not stand in ancestor-descendant relationship cannot exist, because this edge would have then been taken by the depth-first search algorithm, and then U and V would stand in an ancestor-descendant relationship. So this then proves that all edges in this orange tree, all the black edges in the original graph go only between ancestors and descendants in the orange tree. And this will help us to encode these edges into the tree using colors. So if you want to encode the information of this edge, for example, then we can do it by giving the lower vertex, maybe let's call it U, a certain color. And the color will describe that there is an edge that goes from U to the second ancestor of U. The parent, the second parent of U. So if you go up the parent relation twice, this is where the edge points to. This is something that the tree has bounded depth, so there's only a constant number of ancestors that every vertex has, and for every ancestor we can add colors that describe which ancestor the edge goes to. So if you want to be a bit more formal, then we can add some predicates P, I, J, and a Boolean flag that either stands for this one or for this one. And this predicate at a vertex V should mean that there is an edge from V to the ith parent of V labeled with J, and it either goes upwards or downwards. So yeah, remember in G, we had these, the edges that were like this, H, J, and pointing downwards. And this whole information would then be captured by these labels P, I, J, upwards, downwards. And so since there's only a constant, the depth is bounded and the number of labels J is bounded, this is why there's only going to be a bounded number of predicates P, I, J, upwards, downwards that we have to add to the graph to encode all the edges.
Well, I remember the graph we started with. It did not have direction for the edges. Why it is now important to remember directions?
Yes, actually we started with this functional graph G, and the functional graph, it has you can think of it as a directed edge labeled graph. So for if you're at a given vertex, then we have a function hj from u is v. This kind of functional graph is what we have. But so far we ignored these functional symbols and just worked with the Geifman graph in order to build the depth first search tree. But we have to actually encode the whole information of the functional structure into our depth first search tree, since we want to do model checking on functional graph with bounded tree depth. So here, this picture may be a little bit misleading, but actually you should think of each edge as a directed edge with a label that tells you which function is used here. So similar to this picture here. And next, we would have to reconstruct these edges using first order logic. So we started with a graph G and the formula phi of y x bar. And now we've built this functional forest, call it G prime. And we also have to build a formula phi prime of y x bar that holds if and only if the original formula holds on the original graph. So the new formula can only look at this orange forest and the labeling of the vertices, but it still has to evaluate phi. So that's why we will have to encode the edges of the original graph using first order predicates. So whenever the original formula asks whether fj of x is y, we have to, in the new formula, we have to replace this with a gadget that is true if and only if fj of x is y in the original graph. And the new formula, it works. It can check everything in the orange graph. So the first thing we can do is we can check whether x and y stand in an ancestor-descendant relationship. If x is not an ancestor of y and y is not an ancestor of x, then we know that there cannot be an edge between x and y, and this formula here, or this atom, is false. So if x and y don't stand in an ancestor-descendant relationship, then their f of x cannot be y, or the other way around. So the only way where there could be an edge between x and y is if they're an ancestor-descendant relationship like this. So then we could build a very large first order formula that guesses exactly which of x and y is the lower vertex and which one is the upper vertex, and it could guess how many steps we have to go up from x to y. So for example, it could guess that y is the second parent of x, as it is drawn here in the picture. And if the formula has guessed that, then it can look at the label of x and look at the predicate p p2 j and upwards of x. This predicate would tell us whether there is a function like this, fj pointing from x to y. So we have now this gadget construction, which can check whether such a predicate holds in the original graph by only inspecting the bounded, the orange tree that we've built and these auxiliary predicates that we added to the tree.
Oh, then do we make a big disjunction for every P1, P2, P3, P4? Or? Yeah,
the formula would be a big disjunction over all possible ways that x and y could be a predecessor or an ancestor. And we're going to have a separate formula. We're going to replace this maybe with the formula psi of x, y, the formula psi j maybe of xy. And this formula psi j checks only, it's an unsymmetric formula. It checks whether there's an edge from x to y labeled with j. And this formula would then make a big case distinction, which of the two vertices x and y is the lower one and which one is the upper one, and then would check and assume the case distinction. It ranges over all possible i's, and assuming I is 2, it would then check whether P2 of j upwards x holds. Okay, sorry if this was a little bit hand-wavy, but I hope the rough idea of this construction is clear.
Yes, I think I could write it down now if I'd like. Yes.
Okay, so then we can hopefully take a step back again. So we started with this bounded tree depth graph, which actually looks like this, maybe function h1, h2, h3, something like this. And on this graph, we want to evaluate the formula phi. And the construction that I just showed you creates forest G prime and the formula phi prime, which is equivalent. So for every tuple V, if we plug it in here and we plug it in there, we get the same answer. And on this graph, we can then do the quantify elimination for forests of bounded depth. And in this second step, we get now a new forest of bounded depth and an actual quantifier-free formula phi prime prime. And this is all that is needed for our quantifier elimination procedure. So this brings us then to the very last step of the algorithm, actually performing quantifier elimination for bounded expansion classes. So for bounded expansion, we're going to use low tree depth colorings. And what does it mean? If we have a graph from the bounded expansion graph class, then we can label it with f of p colors, such that every set of p colors induces a graph with tree depth at most p. So here's a picture of it. So here we labeled the graph with 6 colors, such that if we induce the graph only on 2 colors, the graph has tree depth at most 2. And on bounded expansion classes, you can always find such low tree depth colorings with the number of colors that you need. F of p depends only on p. This is going to be the central tool in the proof that I want to show you. And yeah, we have this graph from a bounded expansion class, and we have this formula exists y such that phi holds, where phi is quantifier free. And the first thing we're going to do is we're going to get rid of all the functional stuff that we worked so far. So far, this functional representation has been very useful, but now we have to remove these functional predicates. So whenever we have something like this, like a repeated functional application, such that the predicate which says p of g of xi is xj, then we can replace this with certain edges. And in fact, we're going to use directed labeled edges. So we're going to put a directed labeled edge from xi to a if g of xi is a. So this strange looking symbol stands for a directed edge from xi to a labeled with g, and it simply encodes all the functions g. And we can make a similar function, a directed edge, for the function p. And then this repeated function application, g of x1, p of g of x1 is xj. It is equivalent to stating there exists a vertex I such that you can go from xi to a via such a g edge, and then you can go from a to xj via such a p edge. So it simply encodes the functional predicates using graphs, normal graphs where there's only these directed edges that for which we allow labels now. And this means from now on we can assume that we work with a directed edge labeled graph. But we were making the formula a little bit complicated, so we introduced this existential quantifier over A that kind of encodes the intermediate value of this function application. And if we have, if we nest three functions, then we're going to have like two intermediate values that we need to quantify over. This is why we not only quantify over a single variable y, but instead we're going to quantify over a tuple y bar. So the new formula is now psi of y bar and x bar, and we have to evaluate this formula on a normal directed edge labeled graph G. And how are we going to do that? So the thing that we need to show is we have this formula G and this formula psi of y and x, and we have to show that for every such tuple V, G holds on phi if and only if some new graph G prime and a formula, we call it psi prime of V holds. And this one should be quantifier free. This is what the proof requires us to do. And what we're going to do is now we're going to use our low tree depth coloring of our graph G. So let's assume lambda are the colors of a low tree depth coloring of G, where every subgraph of size of xy colors has tree depth at most p. So p is going to be the number of free variables of our formula psi. And this formula psi, it's an existential formula. And if this is satisfied, then there exists some assignment that maps y maybe to some tuple w bar. So if it is satisfied, then G models psi of w bar v bar. And this is still the case if we induce on the colors of w bar and v bar. So psi is a quantifier-free formula, so it cannot talk about any vertices that lie outside w bar and v bar. So if we induce G on only the colors of w bar and v bar, the formula still holds. And if we induce the graph on these colors, then the induced graph has tree depth at most p, because we have w bar and v bar contains only p vertices. So in particular, they only have p colors, and the subgraph induced on these colors has tree depth at most p. So the case distinction will look somehow like this. We make there exists a V such a G is satisfied on V if and only if you have a big case distinction over all subsets of colors of lambda of size P, and then you require, and S is the name of the subset, and additionally you require that the colors of V are contained in this set S, and then now you can induce the graph on this set S. So the formula holds in the original graph if and only if the formula holds if you induce the graph G on some subset S of P colors. This is by the argument that I just showed you. At least the forward direction of the implication follows from this, and the backward direction follows immediately, I suppose. So from now on, we can restrict our attention to these graphs that are induced only on P colors. And I want to perform now quantifier elimination for this graph and this formula. So by the low tree depth colorings, all these graphs GS, they have tree depth at most P. And this means we can use the existing quantifier elimination procedure for graphs with tree depth at most P. So on this part, we're going to perform quantifier elimination, and what we get is this. So for each different subset S, we did a quantifier elimination. And so for each of them, we get a different graph G prime S and a different quantifier formula psi of S. Note that we didn't just do one step of quantifier elimination, but we did size of Y bar many steps. Because we have to eliminate each of the variables that occur in Y bar. But after we've done that, our formula psi S is going to be quantifier free. And now we have this large collection of graphs G prime S and psi S. And we can assume, first, this graph G prime S, it has the same underlying graph as G, but it uses some auxiliary colors that we added to the graph. And we can assume that these auxiliary colors among all graphs GS are disjoint. And then we can combine the colors all in one big extra graph, which is like all the colors combined. And we can call this graph simply G prime. And since G prime contains all the information of the GS, we can plug it into this formula at every position. And now I agree that this last step is quite technical, but we're almost done, because the very last step that we're going to do is we're going to pull out this graph G, pull it out here in front of the formula. So this property here, that the colors of V are a subset of S and the big case distinction of all colors in lambda, this is something that can be expressed in first order logic. So that's why we can take this and plug it here into the formula. And the result looks like this. This is equivalent to saying that G prime satisfies this bigger formula. And this bigger formula now enforces is a big case distinction over all the subsets of colors and all the psi S. And additionally, it requires that the colors of V are contained in S. So this is something that can be expressed in first order logic. And so this is now the final result of our quantifier elimination procedure. This is a graph with bounded expansion. And this here is a quantifier-free first order formula. And the length of the formula did not grow too much. It is still of size independent of G, because size of lambda depends only on P, and P depends only on our input formula psi. And this then completes the proof. other questions about this? Okay, I believe that this was a bit much to digest. But nevertheless, maybe we then move on, because what we've now showed, we've completed the proof. We've shown with a quantifier elimination procedure for graph with bounded expansion. And this gives us then model checking for bounded expansion in FPT time. And the way we did it, we started with trees of bounded depth, and then we gradually lifted this up to first graphs with bounded tree depth, and then using low tree depth colorings to graphs with bounded expansion. And yeah, very nice. We completed the proof. And this completes what I wanted to say about bounded expansion. I wanted to wrap up this algorithmic section by also talking about nowhere dense graphs. And the general rule is that things that work for bounded expansion also work for nowhere dense graph classes, but in a slightly uglier way. And the ugliness for nowhere dense graph classes is in this case that we don't know how to do quantifier elimination. So this is a big open question, doing quantifier elimination for nowhere dense graph classes. So far, nobody knows if and how this is possible, but there is a different proof that sidesteps this, that still shows that you can do first order model checking in FPT time on bounded expansion classes. So let's compare nowhere dense classes and bounded expansion classes. So for bounded expansion, you have these P tree depth colorings. If you want to have every subset of P colors to have tree depth P, you can achieve this by coloring the graph with f of P many colors. So the number of colors that you need depends only on your threshold P. On nowhere dense classes, you can get something similar, but not quite as nice. So if you want to have a P tree depth coloring, then you need to use more than f of P colors. The number of colors that you should use are now f of epsilon and P times n to the epsilon. So now the number of colors suddenly depends on the size of the graph. So n is the size of the graph that you want to color. But the strange thing is now that you can make the epsilon as small as you want. So if you want to use only n to the 0.000001 colors, so a very, very small polynomial in n, this is possible. The cost that you have to pay is now that the function is also f of 0.00001 and p. So the f can grow quite a bit, but the polynomial dependence in n can be shrunk as low as you want it to be. So an example for such a function would, for example, be log n. So log n can be bounded by n to the 0.001, and here it can be bounded by n to the epsilon for every epsilon, at the cost of having this additional error term of epsilon next to it. And now, if in the bounded expansion case, you want to enumerate all the subsets of size p, you can do this in time p choose f of p, which is constant as long as p is constant. But for nowhere dense classes, this term looks quite a bit more ugly. You have now p choose this strange term, but this can be bounded by putting simply the p here in the exponent, and you then get f of epsilon p times n to the epsilon p. And now you can use the fact that the epsilon can be made as small as you want it to be. For example, you can replace epsilon with epsilon prime divided by p. So if you substitute it, then epsilon p gets replaced with epsilon prime, and you end up with such a running time. So even enumerating p subsets can be done in time, in some function of epsilon, and p times n to the epsilon. So such a subset enumeration that was crucial for our algorithm is possible, and the size is rather small, but it's no longer constant. So if you only want to do that, that's fine. But if you want to do something more expensive, like something with the running time 2 to the 2 to the f of p, this is possible in bounded expansion classes, but in nowhere dense classes, this is no longer possible, because 2 to the 2 to the n to the epsilon, this is still larger than 2 to the 2 to the log n, for example, which is still larger than, which is the same as 2 to the n. So these kind of expensive operations, they don't work anymore on nowhere dense classes. That's why I have to be a lot more creative here. Okay, so yeah, we gradually define more and more complex graph classes, and nowhere dense has been so far the limit. You can do model checking on this kind of graphs. And next we could wonder whether this is the best you can do or whether you can go beyond nowhere dense graph classes. And we show that the answer here is no. So we show that with nowhere dense classes, we've basically found the most general sparse graph classes for which first order model checking is still tractable. So this is a very strong statement. And in order to show it, we have to put some meaning into the word sparse. So I said it's the most general sparse graph class. And what does it really mean to be sparse? In our case, we say sparseness is mostly captured by a monotonicity. So we say that the graph class is monotone if it is closed under removing vertices or edges. So if you're in the graph class and you remove some vertices or edges, you can only make the graph more sparse. So for sparse graphs, this seems like a reasonable assumption that you are allowed to remove edges because it should only make you more sparse. And now this is a beautiful result, which states that for monotone graph classes, the class C is nowhere dense if and only if first order model checking is FPT on this graph class. So now you have an exact characterization of those classes where you can do FPT model checking, assuming that you restrict yourself only to monotone classes. And this here, it's a standard complexity theoretic assumption, and everybody believes this to be true. And now I want to show the backward implication of this. So I'm not going to show that you can do first order model checking on nowhere dense classes. This proof is quite complicated, but I can show you that you cannot go beyond nowhere dense graph classes, at least in the monotone setting. Are there any questions so far? Okay, then in order to show you that you cannot go beyond nowhere dense graph classes, I need to introduce some more formalism. So we already defined our depth R minus. Now I'm going to define depth R topological minus. And these are graphs that you can build by the following operation. You can choose some nails or principal vertices, and then you can pick internally vertex disjoint paths of length at most 2R plus 1 that connect the nails. So these purple paths that I've chosen, they need to be vertex disjoint except for their endpoints. And if you then contract these paths, this is what we call a depth R topological minor. It's quite similar to the depth R minus that we discussed so far, but it's got a slightly different flavor because now you have to choose paths instead of choosing R balls. But it is quite easy to see that if H is a depth R minor, a depth R topological minor, then it is also a depth R minor of a graph. So here we've seen this embedding of this depth R topological minor, which means that each of those paths of length at most 2R plus 1. What we can then do is we cut this path in half and take the path and put it into the depth R balls of the closest vertex. So by splitting these paths accordingly, we get these depth R balls of radius at most R around the vertices. And this is now a model for our depth R minus. So in particular, every depth R topological minor is also a depth R minor of a graph. And we can now use these topological minors to also define our clique size and average degree of graphs. So before, for example, we defined omega R to be the maximal clique size occurring as an R depth R minor, and by putting some tildes above everything, we can instead define omega tilde of R to be the maximum size of a topological R shell or depth R minor. And on the last slide, we saw that if something is a topological minor, it is also a normal minor. And this implies automatically that the size of the topological versions of these measures is bounded by the normal versions of these measures. But surprisingly, you can also do the inverse statement. So you can bound the normal version of these wedge measures as a function of their topological counterparts. So the function starts to look a little bit more complicated, and the subscript can change slightly, but these topological versions and the normal versions of these width measures, they're quite related. In particular, if one is bounded by a function for every R, then the other one is also bounded by a function for every R. That's why we can replace now in the definition of bounded expansion in lower dense classes these normal depth R minus with topological depth R minus, because they're functionally equivalent. If one is bounded if and only if the other one is bounded. And we can now use this to show hardness for graph classes that are not nowhere dense. So let's again use this definition to see what it means to be nowhere dense. A graph class C is nowhere dense if for every number R there exists a number T such that all graphs in the graph class have no KT as depth R topological minor. And now, what does it mean that a graph class is not nowhere dense? So we simply have to inverse the statement. So we say a graph class is not nowhere dense, or in other words, somewhere dense. Here it says for all R, and replace it with there exists an R. And if we replace, take the inverse statement, then it reads as follows. A graph class C is somewhere dense if there exists an R such that for every T, there exists a graph with a KT as a topological minor, R topological minor. So this is now a definition of somewhere dense classes. And a class is somewhere dense if and only if it is not nowhere dense. And the statement that I want to show is the following. If you have a graph class that is nowhere monotone and somewhere dense, then first order model checking on this class is AW star hard. So this just means it is as hard as in general. So we're going to use a small tool now called Ramsey's theorem, which states that if you have first of all, if there's any questions in between, feel free to interrupt. If not, then I would like to mention now Ramsey's theorem, and it states the following. If you have some number T and R, then there always exists an edge coloring of the clique KK with such that Oh no, sorry. Yeah, for every T and R, there exists a number K, such that every edge coloring of the KK clique with R colors contains a monochromatic KT. So you start, you want to have a KT that is monochromatically colored, and that means you start with a KK and color it with R colors. And now every edge has a color. It can be red, green, blue, and so forth. You map it to R colors. And Ramsey's theorem states now that within this colorful clique, you can always find a monochromatic clique of size T. So in particular, if you have very large R-colored KKs, then you also have very large KTs in a graph class. So once again, because it's maybe a tricky statement to digest, if you want to have a monochromatic clique of size T in an R-colored clique, where you color the edges with R colors, then there exists a number K that depends only on T and R, such that an R coloring of this graph KK contains KT as a monochromatic subgraph. This is what Ramsey's theorem states. And we're going to use this as a small tool now. And I want to show you that model checking is hard on somewhat dense monotone graph classes. So that's where we're going to start with some class C that is monotone and somewhere dense. And by the definition of somewhere denseness, there exists an R such that for every T, KT is a topological minor. So you can make the T as large as you want. There's always going to be a KT as R topological minor. Got an R topological minor of size 10,000 million and so forth. Arbitrarily large KT R topological minors. Okay, so we're going to pick this R such that for every T, there is a KT as the depth R topological minor. And this depth R topological minor, it's drawn here on the right. We've got these yellow nails or principal vertices, and each yellow vertex is connected by a path of length at most 2R plus 1. And this subdivision, it is then contained in the graph class. And you can make the T as large as you want it to be. And now we're going to use Ramsey's theorem. So you can interpret this KT, the lengths of the edges as colors. So you can think of this KT depth R topological minor as KT, where the edge color is the length of the path. So each path has a length between 1 to 2R plus 1. This is all the possible length values that a path between the vertices can have. And Ramsey's theorem states us now that there is if you have this large KT, there will be still a large monochromatic subgraph. And in this setting, monochromatic would mean that all the connecting paths have the same length. So Ramsey would enforce that we can pick a large subgraph where every path has the same length, R prime. And in the beginning, we can make this T as large as we want. That's where we can also enforce this graph here to be as large as we want. And so we have this large R prime subdivision in our graph class. And next, we're going to use monotonicity. So we know that the graph class is closed under removing edges, and this in particular means that we can, these extra edges that were there, or this path, if we remove them like this, then we still have a graph from the graph class. So this graph here would still be contained in our graph class C. And it would imply that our graph class C contains R prime subdivisions of arbitrary graphs. Are there questions so far? Okay, so if we do some additional magic, we can even enforce these graphs to have something that we may call hair. So we somehow need to distinguish these auxiliary vertices, and we can do it by enforcing that they have like three pendant vertices attached to them, something that I call hair here. So the vertices that lie on the path, they all have degree 2, but you have these orange, yellow vertices that don't have degree 2. This is how you can distinguish the nails from the remaining vertices of the graph. And if you do some extra work, then even these graphs, they all occur in C. And now we want to show that model checking is hard on C. And we're going to do it by reduction from model checking on general graphs. So let's assume we want to know whether some graph G satisfies some formula phi, and G is maybe this house graph, and phi is some random formula. And we know that this is hard, and let's assume for contradiction that we could do model checking in FBT time on the somewhere dense graph class. And I will show you that this implies that you can evaluate this formula here on the graph G in FPT time. So what we're going to do is we take this house and subdivide it R prime times. And we're going to add the hair to the vertices. The result will be contained in our graph class C. This is what we showed on the last slide. And this is also where we need Ramsey's theorem. So we're going to construct this graph algorithmically. And in order to construct it, we need to know the length of each of those paths. If we didn't know the length of the path, if we only knew that it has some length between 0 to 2r plus 1, then we would have to guess for each edge how many times it would be subdivided, and that would take exponential time. So this would not be good. But using this extra argument using Ramsey's theorem, we know that there is a subdivision of the house where every edge has exactly the same length, is subdivided exactly r prime times, and you additionally can distinguish the nails using this hair, and this exists in our graph class. And now we can do the same trick that we did a couple times already. We can modify the formula in our original formula a little bit. So whenever you ask whether two vertices are adjacent in the original formula, evaluated on the original graph, you now ask whether they have distance at most r in the new purple graph. This is how you obtain phi prime. And additionally, you have to restrict all the quantifiers to vertices with degree at most 3. So whenever you have an existential quantifier, that you replace it with an existential quantifier that additionally enforces that the vertex you quantify over has to degree at least 3. This is what we now use this hair for. It makes sure that we only quantify over these yellow vertices.
So quick question.
Yep.
We know there is an R prime, but we don't know which it is, right? How do we?
That's a very good point.
How do we get the right one?
So we don't know what is the right R prime. We only know that it exists, but we know that R prime is small. It is bounded by some function It's actually a constant that depends only on the graph class. So we could, for example, just try out all values r prime. It will, because r prime will be small, we will only have a few values that we will have to try out.
So we build this into our formula, or we will build different graphs?
We will build different graphs. So for each r prime, we'll build a different graph and a different formula. And we're going to start with r prime equal to 0, 1, 2, 3, and so forth. And at some point, we will find the right r prime such that the model checking algorithm actually runs efficiently. But since we don't know what is the right r, we may have to run all the model checking algorithms in parallel, and one of them will be the right model checking algorithm, and that one will terminate quickly.
So there is one small technical condition that it might be that the model checking might terminate but give wrong answers, right?
Yeah, this is something we talked about a lot recently. That's true. Yeah, I don't know how to deal with this issue right now. Good point.
So maybe you can build it into the formula in some way, that you say the distance between two hairy vertices is at most r. So we know the maximum r that there can be. Maybe you can do it this way.
Yeah, but you still have to try out all the different graphs.
Ah, yes. Okay, I don't know then.
Okay, but yeah, if we assume this detail is solved as well, then the proof would be complete. This new graph, assuming that we guessed the right r, is contained in R class C, and that's where we could do FPT model checking on this graph. And if we guessed the right r, we would then get the right answer to our original question in the original graph, because the formula was constructed in such a way that is equivalent to the original formula on the original graph. And this then completes the proof, I suppose. So it shows that for monotone graph classes, we cannot go beyond nowhere dense graph classes. So for nowhere dense graph classes, this is kind of the limit. It is a very natural definition of sparse graphs. But it says nothing about dense tractable graph classes, such that a class of all cliques. So if you have a monotone graph class that contains all cliques, then in particular, it also contains all graphs. So if you have a very large clique and it's closed onto subgraphs, then also all the subgraphs of these cliques are contained, and you would contain all the graphs that there are. So this is why the result that we just discussed says nothing about model checking on the class of all cliques. So the class of all cliques, it's a very, very simple graph class, and model checking is tractable there. But because we only consider not monotone graph classes, we don't get any results for this. That's why I want to wrap up this lecture with the long-term goal that the community is working on right now, is trying to find tractable graph classes that not only capture sparse graphs, but also capture dense graphs as well. So I suggest we are 1 hour and 20 minutes in. Let's take a quick break right now.